Okay, the video, multiple choice. Question 1, it's just Newton's second law, guys. Basically, Newton's second law, F equals delta mv over t. So it has to be a force, and D's the only force. For part 2, or question 2, obviously conservation of momentum. If we have conservation of momentum, then y is going to have to be equal and opposite to x because they're going in opposite directions. 3, sorry. This is a conservation of momentum, but the key word here is elastic. Now, in order if you have an elastic collision, sorry, the relative speed of approach is equal to the relative speed of separation. So you basically run that first and then apply the rules of conservation of momentum. And as they're the same mass, the only way you can have the same speed of separation and the same speed of approach is if this one stops and this one cracks on. Okie dokie, moving on down. Question 4. The defining equation for simple harmonic motion is the acceleration is proportional to the displacement. A equals minus omega squared x, or minus 2 pi f squared x. Therefore, the maximum acceleration will be when x is a maximum, and we can say A max is 2 pi f squared a, the amplitude. Now, once you get to this is proportional to that. Therefore, we get D. Going back to that equation, the defining equation for SHM, well, that basically leads us to this idea here that when x and a are proportional to each other, and there's a negative correlation, because obviously when that's in the positive quadrant, this is in the negative. Hemisphere. Next up, here's your particle. It gives you all the mass. It tells you the time to make 50 oscillations. We want to find the velocity. Kinetic energy is a half mv squared. We're going to have to put in this term for v. Remember, if you think back to, so that should be a v. Remember the very first equations of SHM, we'd say that the displacement was a sine x, or sine 2 pi f, and then you differentiated that to get the velocity. And the long and the short of it, it's in the formula sheet anyway, the long and the short of it, the maximum velocity is 2 pi fa, okay? And this is asking what the maximum k is, we want the maximum v. So put that lot in, make sure you square it. When you do that, of course, this is 2 pi divided by the time period, so we're going to get the frequency. And chuck that in, and it comes out to 2.5 times 10 to the minus 3. Question 7. The simple pendulum has a time period of 1.42. Here's the system. Here's what you do. Basically, t equals 2 pi root L over g. Therefore, the time period is proportional to 1 over root g. Therefore, we'd say the new time would be equal to the old time multiplied by 1 over root of the new g. So it's 1.42 divided by 0.37, which I haven't written it down, but I think it's C. Okay, question 8. Now this one's pretty cool. The two masses are first obviously in contact with each other. That's the first thing. So first situations they're going to be touching. We therefore know that the separation of their centres of mass would be 2r. Okay, because each one has a radius of r. They're now separated, so the force of attraction is F over 9. So when they're together touching, there's a force F. That force is now F divided by 9. Now you should know that the force is proportional to 1 over the radius, or the separation, squared. So if this is now divided by 9, the separation, the net separation, should have gone up by 3, because obviously, by 3. Okay, so 3 squared is 9. Yeah. So what we have here is a situation where we can now say that the centre of mass before was 2r, it's now got to be 3 times as big. Okay, so that's 3 times by 2r, so that's 6r altogether. Okay, so there's separation now, where before it's 2r, it's now 3 times as big, so it's 6r. Therefore, the surfaces there are only 4r apart, and because of that, we want. Well, there you go, there's your answer, 4r. Alright. Question number 9. Mass, orbit, height r above the uniform planet of radius r and density p. So we know that the force is F equals g mm over 2r squared. Now remember, this is not this is There's the radius r, there, that's r, and then our object is r above that, so it's got to be 2r in there. That's the key thing. Once you've got that, the rest of it's pretty straightforward. You just basically put this lot in for the mass. Of course, the mass is going to be 4.3 pi r cubed. That's the mass of the planet. Shove that into there, you get r cubed on the top, r squared on the bottom. Sort all that out, and it comes to A. Okay, 10. I like this question. It gives us radius and density for 2 planets. Now, we know, it's basically doing this again, we know that gravitational field strength is g times the mass over the distance squared from the centre of the object. It's doing the same thing as before, basically putting this lot here in for the mass. We basically can again cancel all our stuff out, and what we see is we get a whole load of constants in here, but we get r and p, 1r, 1p. Okay, the product of that, and this is all constants. So we can say that the gravity is proportional to the product of the radius and the density. Now at this point we could probably just stop here, because 8 times 6 is the same as 16 times 3, so we just straight away know that it's the same answer. Okay, but if it was different, then what we would do is we'd say, well, g primed would be proportional to r primed over rho primed, and all we'd do is we divide this lot, and then of course we carry the g across over to that, and that's how you do it if it was the numbers didn't work out that way.